Hi everyone. All right, we're going to do vectors in 3D and we're going to split it into two sections. Okay, so make sure you're paying attention in what section. So points in 3D, it means that we have a different kind of plane. So what we're looking at right here is an XYZ plane. Okay, so X, you're going the direction of a diagonal left to right. And then Y again is the other diagonal left to right, and then Z is up and down. So to kind of show a little bit of what that would look like, think of it like a room where you have, your walls, okay, and then you have a floor, okay. So with plotting points, we're not going to do too much with it, but I want you to see it. If we have a point P2, or that's P and then the 2, 4, 7, so this is your X, Y, and Z. Okay, we're just going to kind of mark these real quick and do your best to make your own. It's not easy to make your own because it looks kind of weird. As you can see to the right over here, it looks kind of funny. But for point 247, you're going to go to your x-axis 2. Okay, you don't have to draw the lines, but I'm just showing you where we're going. So your x-axis is, you're going along it, it's a positive 2. And then you're going to go along your y-axis to 4. Okay, so it's going to be kind of a weird diagonal. And then to go up to your y or your z-axis to 7, 1, 2, 3, 4, 5, 6, 7, it's going to go essentially straight up. Okay, so this is your point P. So if you're looking at point Q, I tried to make my own, and it sort of, it looks okay. But if you have negatives, you can see for negative x, you're going the opposite direction. Okay, positive 3 for your y, you're going the direction that you did before. You're straight ahead, and then for z, you're essentially going down. Okay, because it's negative. So approximately this is what point Q looks like. It's point 3, negative 4, 3, negative 5. Okay, but just so you can kind of see this, because I know you're gonna probably see it in some of your later math. So moving on, distance formula in 3D. So we have these 2 points. We've got P is 2, 3, 4, and Q is 5, 6, 7. If you remember, distance formula for 2 points is just the changes in your x's squared plus the changes in your y's squared. Okay, so it's the same thing, except you have a third point. So the distance for PQ, you're going to take, we'll do a long one here. You're going to take the changes in your x's squared. I'm using my delta that we learned. The changes in my y's squared, and I'm going to take my changes in my z's squared. So changes in your z's would be z2 minus z1. Okay, so similar to what we had before, except now we have 3 points. So for this, my changes in x's, we've got 5 minus 2, x2 minus x1 squared. Changes in my y's, y2 minus y1 squared, and then we're going to add that to z2 minus z1 squared, and it should all be under your radical. Okay, so now we should have 3 squared plus 3, they have now just all be 3, that's just a happy accident. So that should give you square root of 27, which simplifies to 3 root 3. So that would be the distance between those 2 points in a 3D space. Okay, so in a 3D space, that would be the distance, right? So talking about components of vectors in your 3D space, again, we have the idea of your initial point which is also called your start point. So if you want to know what initial is, it's your start point. We're going to say that's P. And we're going to use the same P as before. So 2, 3, and 4. And then you should have a terminal point. And we used that word before. So you have a terminal point, which is just an endpoint, and that's going to be Q. And Q is going to be, again, 5, 6, and 7. So to find the vector, because that's essentially what we're doing, we're taking these two points and we're finding the vector, and I'm going to label it vector V, which is just, remember, vector PQ. We take the changes of our x's, the changes of our y's, and the changes of our z's. Okay, that's what we did before with, if this was just 2 points, we would take the changes in our x's and the changes of our y's. Now we're just adding in a third point to it because it's a 3D space. Instead of 2D, it's 3D. So my vector is going to be the x2 minus x1, y2 minus y1, and z2 minus z1, which again happens to be 3, 3, 3. Okay, and that's your vector. Okay? Again, it's the same as before, except you're including z. Okay, that's because we have this 3D space, so now we have an extra coordinate. So, excuse me. So magnitude, if you remember, is essentially your distance formula. Okay, but it's called something different because we're using vectors. So we have our distance formula, and before, if we found the magnitude, it would be the changes in our x's squared plus the changes in our y's squared, and we'd add them together, and we take the square root. So we're going to do the same thing, except now, because of 3D space, we now have magnitude equal to not just the changes in our x's plus the changes in our y's. We're adding in that third component for our magnitude. So lucky for us, we already found something similar to this because, again, it's essentially the distance formula. We're going to use the same vector that we were just using. So 3, 3, 3, the one that we just found from the previous example, right up here. I'm just continuing with the same numbers. And I'm going to find my magnitude. Okay, so I know the changes in my x's are 3, so I'm going to square it. The changes in my y's happen to be 3, and the changes in my z's happen to be 3. Okay, so I don't need to do all that math again, it's already there. So this should be square root of 27, which happens to be 3 root 3. Again, it's the same as distance formula, but because it's vectors, we call it magnitude, right? So that's finding magnitude in your 3D space. So now vector operations. Okay, vector operations. Okay, order still matters. Okay, order still matters. So for vector operations, we're going to use two different ones now. We're going to use vector u, which is -1, 2, -3, and vector v, which is -4, 6, and 7. You probably thought I was going to use 4, 5, and 6. I tripped you up a little bit. So for vector operations, remember we would do addition and subtraction. So we're going to add vector u to vector v. So if you recall this from before, you would take your x's and add them together. You would take your y's and add them together. So guess what? You're going to take your z's and add them together. So the 3D space just adds one more piece of work for you to do. So for here, we have -5, 8, and a +4. Okay, so that's addition. Okay, it's all the same thing. So if I was doing subtraction, again, this is why order matters, because you're going to take the x's from u and subtract the x's from v. You're going to take the y's from u and subtract the y's from v. And you're going to take the z's from u and subtract the z's from v. So order does matter, so make sure that v, because it's after the subtraction sign, is, after the subtraction. So we have, this changes to a plus, so this should be a plus 3. We should now have a negative 4, and then this should be negative 10. Okay, so that's addition and subtraction. And then if you recall, we did a scalar, okay, because you can kind of mix up these operations and do them all together. So we're going to do a scalar with this as well. So we would take our scalar and multiply our x's, scalar multiply our y's. I'm struggling here. So 2, and then our scalar and multiply our z. Okay, so it just adds another number in there, so you just can't forget it. So that should be positive 4, negative 8, and a positive 12. All right, so that's vector operations. That's exactly what you would do for each of them. The only difference now is that you have 3D space, so you have that extra component of z. And that's the end of part 1. So part 2 will pick up with I, J, and K. Have a good day.